friends, welcome to Bond with RK Chemistry YouTube channel. In this video, I am going to explain the homogeneous catalytic hydrogenation reactions. These reactions have advantages over heterogeneous catalytic hydrogenation reactions. These reactions are highly selective when compared with the heterogeneous catalytic hydrogenation reactions. And also these reactions can be performed under ambient temperature and pressure. The most commonly used homogeneous catalyst is Wilkinson's catalyst. The chemical formula of Wilkinson's catalyst is it's a rhodium complex, rhodium, Cl, triphenyl phosphine 3 times. The IUPAC name of this complex is chlorido tris triphenyl phosphine rhodium, and the oxidation state is 1, rhodium 1. This is the IUPAC name of Wilkinson's catalyst. Wilkinson's catalyst, it's a square planar complex. This is the structure of Wilkinson's catalyst. The metal is rhodium. The ligands are chlorine and triphenyl phosphine and triphenyl phosphine. It's a 16 electron complex. It's not 18 electron complex. It's 16 electron complex. Since it's a 16 electron complex, it's coordinatively unsaturated complex. 18 electron complexes are saturated complex, coordinatively saturated complex. 16 electron complexes are coordinatively unsaturated complex. Since all the electrons are paired, it's diamagnetic in nature. The behavior is diamagnetic, and the color, it's a solid. The color of the Wilkinson's catalyst is dark red brown color. And Wilkinson's catalyst, it is soluble in organic solvents such as hydrocarbons. This one is soluble in hydrocarbons such as benzene, and also it is soluble in ethers such as tetrahydrofuran, and also soluble in chlorinated solvents such as carbon tetrachloride. Since Wilkinson's catalyst is soluble in solvents, it's a homogeneous catalyst. Wilkinson's catalyst selectively reduce C double bond C and C triple bond C. The remaining bonds such as C double bond O or N double bond O or C triple bond N or N double bond N, these types of bonds cannot be reduced by Wilkinson's catalyst. These C double bond C and C triple bond C can be reduced by Wilkinson's catalyst. This one is very selective. It cannot reduce the functional groups which have C double bond O, N double bond O, C triple bond N and N double bond N. The reactivity of Wilkinson's catalyst depends on stability of alkanes. It is indirectly proportional to stability of alkanes. More the stability of alkene, less the reactivity of alkane. So the reactivity order will be ethylene. This one is most reactive among the alkenes, greater than monosubstituted alkene. This one is monosubstituted alkene is greater than cyclohexene is greater than disubstituted alkene. Both are groups on same carbon, disubstituted, geminal, and another disubstituted alkene cis form R, R and H, H. This one is cis disubstituted, and the next one is trans hydrogen R. Hydrogen R. This one is trans disubstituted. Next, trisubstituted R, 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 H is greater than tetrasubstituted. As a substitution increases, stability increases, reactivity decreases. In the case of Wilkinson's catalyst, as the number of alkyl groups increases, it's very difficult to reach C double bond C by Wilkinson catalyst. That's why there is a decrease in reactivity as the increasing number of alkyl groups around C double bond C. Selectivity of Wilkinson's catalyst. We know that Wilkinson's catalyst is highly selective, less reactive and highly selective. It can reduce only C double bond C and C triple bond C. Among C double bond C, more reactive C double bond C, C double bond C will be reduced over less reactive C double bond C. Suppose if you take less substituted alkene, less substituted C double bond C and more substituted C double bond C, less substituted C double bond C will be reduced over more substituted C double bond C. Suppose if you take this molecule, in this case this double bond C is less substituted C double bond C. This one is more substituted C double bond C, C double bond C. When you react with Wilkinson's catalyst, triphenylphosphine, hydrogen. Let's take the solvent is benzene. In this case, the less substituted C double bond C is more reactive. So the less substituted C double bond C will be reduced and there is no reduction of more substituted C double bond C. So you will get here there is no reduction of more substituted C double bond C. If we take the reactivity of cis alkene is greater than trans alkene. So the cis C double bond C will be reduced to our trans C double bond C. So if you take this molecule, okay, this one is trans C double bond C and this one is cis C double bond C. Okay, in presence of Wilkinson's catalyst, and hydrogenation in presence of benzene, Here the cis one is more reactive, the cis C double bond C will be reduced. So there is a formation of here the double bond C double bond C will not be reduced. This C double bond C will be reduced to C single bond C. Exocyclic C double bond C is more reactive than endocyclic C double bond C. The exocyclic C double bond C will be selected for the reduction in case of Wilkinson's catalyst and compared with the endocyclic C double bond C. Suppose if we take this one, the same conditions. Here this one is endocyclic, this C double bond C is endocyclic C double bond C, this one is exocyclic C double bond C. Outside the ring, inside the ring. Exo means outside the ring, endo means inside the ring. Since exocyclic is more reactive, the exocyclic C double bond C will be reduced. So in this case, we will get this molecule. When polyalkene contains isolated C double bond C and conjugated C double bond C, conjugated C double bond C, the reactivity of isolated C double bond C is greater than conjugated C double bond C. Suppose if you take a polyalkene which contains isolated and conjugated. Here this one is isolated C double bond C. These two are conjugated C double bond C. So the isolated is more reactive. So in presence of Wilkinson's catalyst, and the hydrogen benzene, here this C double bond C will be reduced. The reduction takes place at isolated C double bond C. Alkynes are more reactive than, the reactivity of alkynes is more when compared with the alkenes. So that C triple bond C will be reduced to our C double bond C. Suppose if you take this molecule, this is C double bond C and this one is C triple bond C. In presence of Wilkinson's catalyst, H2 dissolved in benzene. Alkynes are more reactive than alkanes. So C triple bond C will be reduced to our C double bond C. Suppose if you take the molecule which has C double bond C and C triple bond C, this one is terminal C double bond C, this one is terminal C triple bond C. In presence of Wilkinson's catalyst, here there is a reduction of C triple bond C. There is a reduction of C triple bond C into C double bond C. So there is a formation of alkane. If the molecule contains two rings and each ring contains a double bond, If one of the ring is attached with electron withdrawing groups such as NO2 or CN, the double bond in which the cycle attached with electron withdrawing group will be reduced in the case of homogeneous catalytic hydrogenation reaction. So here this functional group C double bond C will be reduced. Since NO2 or CN, these groups will be coordinated with the metal atom in the Wilkinson's catalyst. This double bond will be reduced. And some groups like CO, N double bond O, or C triple bond N are aryl groups. These groups cannot be reduced by Wilkinson's catalyst. Let us take a molecule which has these functional groups. Benzene ring it has, and also some NO2 group. Let's take CN group, and here there is a C double bond C. In presence of Wilkinson's catalyst hydrogen, the solvent is benzene. Here the C double bond C will only be reduced. Remaining functional groups will not be reduced. So you will get NO2 and Cn. These NO2, Cn and the benzene ring will not be reduced by Wilkinson's catalyst. Stereochemistry of Wilkinson's catalyst, homogeneous catalysis. There is a syn addition takes place. Syn addition takes place. Suppose if you take malic acid H, CO2H and H, CO2H, when you deuteriate it in presence of Wilkinson's catalyst, there is a syn addition of deuterium takes place. So here there is a syn addition, deuterium, and this one is CO2H, and this one is hydrogen, CO2H and hydrogen. In this case you will get only meso compound. Suppose if you take trans 1 fumaric acid, CO2H, H, CO2H, H, this one is trans. Under similar conditions, here there is a formation of racemic mixture. When deuteriums attach to C double bond C from this side, you will get D, and also from this side also there is a possibility of attaching of D's. So in this case you will get CO2H and hydrogen, here hydrogen and CO2H. In this case you will get H and CO2H, CO2H and hydrogen. Here there is a formation of racemic mixture. If the molecule has aldehyde functional group C double bond OH, the Wilkinson's catalyst cannot act as catalyst. Since C double bond O will be attached with Wilkinson's catalyst, there is a formation of another complex, highly stable complex. That complex cannot be converted into Wilkinson's catalyst. Let us take an aldehyde RC double bond OH. Okay, when you react with Wilkinson's catalyst, sodium Cl triphenyl phosphate, this Wilkinson's catalyst will be converted into there is a formation of RH, there is a decarbonylation takes place. Decarbonylation takes place, and here there is a formation of new coordinate complex RCHCl CO triphenyl diphenyl phosphate. One of the ppH3 will be replaced by the CO ligand. This one is highly stable. It cannot be converted into Wilkinson's catalyst. So in this case, the catalytic property of Wilkinson's catalyst will be lost and it can act as a non-catalyst. It can convert aldehydes into alkanes, but it cannot act as a catalyst. Thank you.